Hi. It's really a great pleasure to meet you guys all online. So thanks, Rose, for the great introduction. I'm currently working at CSIRO, and I'm going to talk about piece of work using machine learning to predict peatland greenhouse gas emissions in face of water-table drawdown. I started this work while I was at ICE with a lot of help from colleagues from France and also collaborators across Europe, from China and from the United States. I hope you guys will enjoy my talk. So I'm really a big fan of the peatland or wetland in general. So I'm going to, I spent several years in Florida. We have the Everglades National Park. It's a 1.5 million acre preserved wetlands. It's a really amazing place. It hosts quite a large variety of wild species. It preserves the purifies water and provides a lot of natural resources, and particularly to climate change. Yeah, that's quite important because it stores quite a lot of carbon. Unfortunately, so the peatland in general, the water table depth is lower in current period of time compared to the historical time. Here, this is a figure shows the average water table depths across European peatlands through time. This one here, so can you guys see my point? The mouse?
I cannot.
You couldn't see the mouse.
Oh wait, yes, now I can. Yeah. Sorry, I can see the red dot.
That sounds good. Yeah. So basically, here is the year 1751. As you can see, as the starting of the industrialization, the average water table depth across European peatland keeps on dropping. So in general, European peatlands are drier now than they were before. The European peatlands are not unknown. So here I show a map of the decline of the groundwater height that has already reaches the environmental limits. This map is not specific for the peatlands, but it can give us a sense that the water table drawdown is quite widespread across different regions of the world. For peatlands, the drawing, the knowing of water table is associated with the acceleration of the loss of the peat, either through very natural processes such as microbial decomposition or through increased frequency of fire. Well, the acceleration of loss of peat is put quite a big threat into our climate system. So people have been studying the impact of water table drawdown on peatland greenhouse gas emissions for decades. Some people generally think that water table drawdown will bring the peatland to be a source because of the increased carbon dioxide emissions from organic matter decomposition. But there are also studies point to the peatland act as a carbon sink because of the filter experiment indicate that actually knowing water table stimulate the vegetation growth, which takes up more carbon dioxide from the atmosphere, and also it reduced the methane and other greenhouse gas. Generally, to study the impact of water table drawdown on greenhouse gas emissions, people can conduct water table manipulation experiments. By water table manipulation experiments, people try to keep other factors as similar as possible, except the water table. They manipulate water table and say what's the response of the ecosystem. Some of the manipulation experiments are carried out in a field condition. In those field conditions, sometimes the water table are naturally differ. Sometimes they are artificially altered. Some of the experiments are more controlled in a semi-natural environment. People normally call it microcosm manipulation experiments. In both of those experiments, they kind of like measure the carbon dioxide or methane or other greenhouse gases under the high water table treatment versus the no water table treatment. So I used the difference of the greenhouse gas emissions under high versus no water table as an indicator of the impact of water table on greenhouse gas emissions. Here, I put the carbon dioxide and methane together to see the net effect on the overall greenhouse gas emissions. For now, we neglect the nitrous oxide. So we collect those data are related to water table manipulation experiments. We tried our best to collect as many data points as possible. So basically, we identified our targets through the searching the keywords through those very common global database, like the ISI Web of Science database, and also other resources. And we removed the duplicates of the studies and also removed some of the studies that didn't fall into our selection criteria. In the end, we get around 400 data points or studies for the carbon dioxide and around 500 studies for methane. Well, it's relatively a small data set compared to quite a lot of classical machine learning studies. But for this type of experiments, the manipulation experiments is really already a decent number of studies. Most of the studies are located, concentrated around Europe and North America. And we do have very limited studies in tropical regions where quite a lot of peatlands are located. And also in Siberian peatlands, we do need more studies. But generally, our compiled studies covers different peatland ecosystem. So for the machine learning model, we used random forest. We trained the random forest through those data points, and we used Python software of Skynet, particularly the random forest regressor. We select around, we consider around 40 predictors, which covers generally the soil characteristic, the climate condition, topography, and also the water table depths before the manipulation, and the magnitude of water table manipulation, and also the greenhouse gas emission before the water table manipulation. We selected the predictors based on the criterion. We say we prefer the model with a highest R square and the lowest root square mean error. So we rely on the leave one out cross validation for our model and predict selection. So it's quite common used during the machine learning study. So here I plot the observed versus the modeled result for carbon dioxide on the left panel and methane for the right panel across the global data points. And so actually a lot of our data points are concentrated in the northern hemisphere, and we don't have much data for the tropical regions. So people may question whether our global model represent well for the tropical region. We also conduct an even-out cross-validation for the tropical studies. It seems that even though we don't have much data to train the tropical response, the cross-validation show a comparable performance compared to the region we have a lot of data for training. So what is nice is we can look into the response of response curve. So basically for the carbon dioxide, the carbon dioxide flux before the water table manipulation, the magnitude of water table depths, or the water table depth manipulation, and the water table depth before the experiment are the top three predictors for carbon dioxide. For methane, the flux before water table manipulation, the magnitude of water table manipulation, and the water table depths before manipulation are the top three predictors. So the right line are the average response curve, and each of the gray line correspond to the response curve for each of the individual experiments. So sorry, the green line is not that clear, but if people are interested in each of the individual study, they can look into each of the response curve to figure out what's the reason and why they have this type of response. And also the response curve are actually quite different across the studies, the individual studies, and in different range of the predictors that actually captures the heterogeneity of the ecosystem response. And here I shows other predictors. They are less important than the top three predictors I showed before, but they have quite a lot of ecological meanings. So this one is for the carbon dioxide. As you can see, most of the response are actually quite nonlinear. This kind of nonlinear response is quite difficult to be captured by a lot of linear methods that are applied in ecological studies. And also here is a map, is a figure shows the response curve for other factors for methane. So you see that the variation of the average response curve is not big. This is because quite a lot of variation are explained by the top three predictors I showed before. So depending on what kinds of information people are interested in, we can also group those individual response curve into different groups. Here is an example by region. So the red line corresponds to the response from the tropical region, and the color with sign, the line is from temperate and boreal ecosystem, and the blue is from the Arctic ecosystem. It really depends on whether people are interested in the region or other groups. It's quite neat to group them together and to provide us some information we can look into. And we can also group it by different peatland types. So based on those machine learning model, we did a feature prediction to say the response of carbon dioxide or methane emission to future table drawdown. So we combined different machine learning models and also with different combinations of those predictor variables. Both of all of those predictor variables, we can get an approximation at a global scale. So in this way, we can make an ensemble global prediction. And here I show the spatial and latitudinal distribution of carbon dioxide and not this is not carbon dioxide, the light response greenhouse response to future table drawdown under RCP 8.5 and RCP 2.6. So under RCP 8.5, which is a scenario if we don't do any actions to mitigate our fossil fuel carbon dioxide emissions, we will face a future that the peatland will contribute more greenhouse gas into the atmosphere. That's a positive feedback. In order to stop those positive feedback, we need to preserve those pristine wetlands and also to restore those drained peatlands. So this is a small exercise I explored through the machine learning. So reflect on the exercise, I feel that the machine learning algorithms is really very helpful, especially for those studies that are characterized by quite a lot of nonlinear response and also very complex interactions. But on the other hand, the machine learning algorithm or method is really very data intensive. So in this way, we need to collect as much data as possible. And we frequently run into overfitting issues. And I also run into issues that I have bias in either the low or high end. To cope with those issues, I think, well, the representation of the data set is really quite important. If the data can well represent the study you are interested in, it can save a lot of trouble. And also it's really good to use meaningful predictors, those predictors that we know now are linkage to our response. Well, it's not really a good practice to put as many predictors as possible. Sometimes it really messes things up. So for this study, I have very limited data points. So this is not really seems like to be suitable for applied the machine learning model, but we can actually generate some pseudo data to cope with those type of study that has limited data points. So I think that's all from my side. Thanks a lot for your attention.